It's my pleasure to introduce Professor Chuxu Zhang. He is a tenure track assistant professor in the Department of Computer Science at Brandeis University. His general research interest is on AI, machine learning, and data science. He has focused on developing effective, efficient, safe, and generative machine learning models and algorithms on graph data and multimodality data. He also applies machine learning to solve challenges in healthcare, social media science, and others. Today, Professor Zhang will be presenting on graph machine learning effectiveness, efficiency, and safety. Welcome, Professor Zhang.
Okay. So thank you for the host, the invitation. So my name is Chuxu Zhang. I'm currently an assistant professor of computer science at Brandeis University. So today I'm very happy to be here at the ICBS conference. So my talk is about graph machine learning. So first, I would like to spend 1 or 2 minutes to introduce about myself. Right? So I got my bachelor degree at China. Then I went to USA for master and PhD study. So I did my PhD study at University of Notre Dame under the supervision of Professor Nitesh Chola. So during my PhD study, I mainly work on data mining, social network mining. So I mainly published a paper in top conference in the data mining, such as SeekKTD, Triple W. And during my PhD, I also interned several times at the industry company, such as Microsoft Research and NEC Labs. So after 3 years of PhD study, I went to Brandeis University as an assistant professor of computer science. So during this period, I mainly work on graph machine learning research and large language model, and also AI for society research. So in this period, I mainly published a paper in the top conference of machine learning and also some papers in the top conference of data science. So here are some represented award I received in the last few years. Right? So in the next month, I will join University of Connecticut, UConn as an associate professor of computer science. Okay. So yeah, you can see no matter which period, social network undergraduate study, I work on network science. PhD study, I work on social network mining, and also uh, uh, assistant professor periods, I work on graph machine learning. You can see no matter which period, there's a common word, right? There's an overlap word in my research topic, that is the graph data, or you can also call it the network data. So graph data is, you can see this is an example of the graph data. Right? So it's quite a simple data structure. It includes two basic elements. The first one, node element. The second one, LG element. So we can use node to represent entity, right, for the data in the real world. And then we can use LG to represent the relationship between any two entities, right? So the graph data can be used to abstract or to model our interconnected world in various domains and various applications, right? Like social media, like Twitter, Twitter, right? And also Facebook and LinkedIn, and also Weibo in China, right? We can use social network or social graph to represent that social media data. And in the public health domain, we can use a public health network, right? We use the node to represent the different entity like a patient, drug, pharmacy, doctors, right? And then we can use LG or relations to represent the different relationship among these different entities, right? And in the neuroscience, we can use the network data or the graph data to represent the connection between different region of the brain of different neurons in the brain, okay? And in the science or the healthcare domain, we can use, there is a basic element in the science and healthcare domain, which is molecular. And we can use molecular graph to represent this kind of molecular data. So for the molecular graph, we use, node to represent the atoms, and we use the LG or the relation to represent the bond between any two atoms, right? And in cybersecurity or Internet of Things domain, we can use cyber networks, right? Or the Internet of Things network to represent these data, right? And also, even in the AI domain or the computer science domain, we can use graph data. Like in the computer vision domain, there are some kind of technique called the scene graph generation, right? We try to generate a scene graph or an images, right? So we can use the graph data to represent the relationship between different components or different partition in images, right? And also, we in the natural language processing, right? A very popular topic is the knowledge base or the knowledge graph. So we can use the graph data to represent the knowledge base in the natural language processing. Okay, so you can see that the graph data can be used to model or used to abstract real world data in different application domains, right? And so like the text data in the natural language processing or the image data in the computer vision domains, right? We can, based on the graph data, we can develop some AI and machine learning model for different applications like classification application, prediction application, anomaly detection application, or recommendation application, or more recently, the generation application, okay? Right. So I mainly work on solving these three challenges. One, we develop AI model or the machine learning model on the graph data. So the first challenge I try to solve is usually the real graph data is complex data, right? So this complex involve three dimensions of complexity. The first one is complex structure. The second one is multimodality features. The third one is dynamics. So later I will talk more about the complex data challenge. And the second challenge I work on is the limited resource challenges. So usually, collecting the label data or annotated label is the challenges, right? This is also same for the graph data. So the first limited resource challenge is that one, we only have limited label data, right? And the second limited resource challenge is, unlike industry company, they have a lot of computing resources, right? But in the academic lab, especially in the university, we only have limited computing resources, right? So how can we only use limited computing machines to develop effective and efficient graph machine learning model? Is the second resource, limited resource constraint challenges, right? And the last one is about the safety challenges, right? So like the large language model, right? The graph machine learning model also have some safety issues, right? When there are some noise data, some bias or sensitive data, and also how to develop an interpretable or explainable graph machine learning model, right? So the third challenge I try to work on is about the safety of the graph machine learning. Okay, so to summarize, right, to handle the complex data challenges, right, which include complex structure, multimodality feature, and dynamics, I hope we can build a framework for effective learning on the graph data. And the second one, for the limited resource constraint challenges, including two kind of resource constraint. The first one, label constraint. The second one is computing resource constraint. How can we build a framework for resource efficient learning on the graph data? So that is the second task. And for the third task, right, in face of these safety challenges, right, how can we build a framework for safe and trustworthy learning on the graph data? So by combining these three goals or three tasks together, right, the overall goal is to develop an effective, efficient, and safe learning framework for graph data in the real world application. Okay, so in the remaining of this talk, I will briefly go through the work in my group for solving these three tasks. Okay, so the first task is build a framework for effective learning on the graph data. So as I mentioned just now, right? So I summarize the three challenges in the real world graph data. The first one is usually real world graph data involve heterogeneous structure. So when I say heterogeneous structure, it means that there are multi-type of entity and relation in the real world graph data, right? Like in the healthcare network, we have different type of node, we have different type of relation. And in the molecular graph data, we have different type of atoms and different type of bonds. And in the cyber network, we have different type of devices and different type of relations among different devices, right? And so this is the first challenge, data challenge, heterogeneous structure data. The second one is multimodality content challenges, right? So each node or each edges in the graph data can be associated with multimodality content like tabular attributes, image attributes, or text attributes, right? Like for example, in the Weibo or in the Twitter, you can the social user, right, can post the text data and can also post the image data, right? So that is means that this kind of social user can be associated with the multimodality feature or multimodality data. Okay, and the last one is usually the real world graph data is dynamics. So when we consider about the healthcare network, right, the patient visits a doctor or take a drug at different times, right? You can see each relation is associated with a timestamp information. That means the graph data is a dynamic data. Okay, and also the communication between different devices in the cyber network or the Internet of Things network is dynamics. Okay, so by consider these three data challenges together, we introduce a concept called heterogeneous graph. Right? So what is the heterogeneous graph? At first, suppose the simplest graph is the homogeneous graph. We have same type of node and they are connected by same type of relations, right? So if we consider heterogeneous structure, then we can use different type of node to represent the different type of entities, right? And different type of entity are connected by different type of relations, right? Then again, when considering the multimodality features, right, we can assign each node as different features. Each node can be associated with multimodality features, right? Like image feature, tabular feature, and also text features, right? And again, by considering the dynamic information for each timestamp, we can build a heterogeneous graph like HG1, HG2, HGT means the heterogeneous graph at different time steps, right? So by connecting the same node at the different timestamp, we are able to build a dynamic heterogeneous graph, okay, or temporal heterogeneous graph. So after introducing this heterogeneous graph or dynamic heterogeneous graph, so we can build AI or machine learning model, right, for solving different applications or solving different tasks on the graph data, like node or graph classification task. In the real world application, it can be a molecular property prediction task, right? If we take the whole graph as a molecular graph, and if we want to predict the label of this whole graph, then it can be a molecular property prediction application. And the second typical application in the graph data is link prediction, right? Link prediction is try to predict the missing link, right, or the preference between two nodes. It can be like a friend recommendation application or the recommended system applications, right? So and another typical application on the graph data is a node regression task. So each node is associated with the numerical values, and we try to predict the numerical values associated with each node. So in the real world application, if we take each node as a patient node, right, then we can try to predict the risk level, right, which is a numerical values for the patient. So it's a typical node regression task. Okay. So currently, the most popular AI or machine learning model on the graph data is called the representation learning model, right? So what is the representation learning model? Right? It's like a representation only on the text data or the image data, right? Given the graph data, we try to learn the feature representation, low dimensional feature representation of each node in the graph. Then after learning the representation of each node, we take this representation as a feature and fit them into a different machine learning model like classification model, regression model, or anomaly detection model for different downstream application, right? So currently the most, maybe many of you knows, right? Currently the most popular graph representation learning model is called the graph neural network models, right? So what is the major idea of graph neural network model? So the typical strategy is called the message passing mechanism. So what is the message passing mechanism? So if suppose here, right, we want to learn the feature representation, low dimensional feature representation of this red node, and we try to do what kind of operation? Try to do neighbor aggregation. So what is the neighbor aggregation? Here actually V represent the representation of node V, that is the target node, and you belong to NV. NV is the neighbor set of this target node, right? So we try to do what? Aggregation of all feature information of this target node, neighboring node, right? So that is, we try to receive the information from the target node's neighbor to learn to aggregate all neighbors feature information to learn the aggregated embedding. So this aggregated embedding is used as the final embedding of the target node, right? So this idea is inspired by something in the neuroscience, right? So when a target neuron generates the signals, right? It usually try to receive signals from its neighboring neurons to generate its own signals, right? So it's quite similar. The message passing mechanism in the graph neural network is quite similar to the something in the neuroscience. Okay, so that is the graph neural network. Okay, so but based on these complex heterogeneous structure, right, we need to build a new message passing mechanism that are able to handle the complex heterogeneous graph data. Okay, so we proposed a few years ago, right? So that is the award-winning paper this year. It's called the Frontier of Science Award, right? Which is have received 1,300 citations, right? It's called heterogeneous graph neural network. So 5 years ago, we built a model called heterogeneous graph neural network model. So it's a novel heterogeneous graph learning foundation framework, right? So unlike the simple message passing mechanism on the homogeneous graph, we introduce still simple, right? Yet effective hierarchical message passing enable aggregation mechanisms, right? So as I mentioned just now, there are 3 data challenges, right? The first one is multimodality feature. The second one is the heterogeneous structure. The third one is the dynamic or the temporal challenges, right? So to solve these 3 data challenges, we introduce 3 layers of aggregation, right? The first layer of aggregation is we try to, introduce a multimodality aggregators, right? To solve the first challenge. Right? And for the heterogeneous structure challenge, we introduce heterogeneous neighbor aggregation mechanisms, right? To solve the second challenge. And the third one, to solve the dynamic or the temporal challenge, we introduce the third layer of aggregation called the temporal aggregations, right? So in the following few pages, I will briefly introduce these 3 layers of aggregation, right? So for the first layer of aggregation, since there are multimodality content, right, in the complex heterogeneous graphs, right? For each type of content, we can use some pre-training techniques, right? So like for the tabular attribute, we can use one-hot encoding. For the text features or the text content, we can introduce the pre-training language model, right? And for the image features or image content, we can introduce the pre-training vision language model. So after we learning the pre-training embedding of each type of features, then we just need to introduce a simple neural network like a one-layer, multi-layer perception to do the fusion of different type of content, right? Different modality of content to get the fused representation, right? So this is about the first layer of multimodality content aggregation, okay? Then for the heterogeneous structure, we introduce another aggregators, right? So the general idea is that we think that a different type of neighbor should contribute differently into the target node embeddings, right? So it's quite a simple idea of attention mechanism, right? So I suppose all of you know attention mechanism. Attention mechanism try to measure the impact of different type of neighbors using attention schools, right? So here we introduce some attention mechanisms, right, to measure the impacts of different type of neighbors, right? I'm not going to talk about the details, right? The details are a little complicated, but the general idea is that we introduce attention mechanism to measure the impact of different type of neighbors, then to do the fusion with weighted fusion, right, with the computed attention school. Okay, so that is the second aggregators, right? And the third aggregator is that transformer architecture is quite popular in modeling the sequential data, right? The temporal data or the dynamic data is the general sequential data, right? So inspired by these, we introduce another transformer encoder to encode the temporal embedding of the same node at different time steps, right? And fuse the information at different time steps to get the final embedding of the target node at the current time step. So you can see that if we want to compute the embedding of step t, then we can need to fuse the embedding of the same node from 1 to t, from step 1 to step t. Okay, so that is the general idea of the third aggregators, right? So yeah, by combining three together, we build a hierarchical. The first page shows, right? We build a hierarchical message passing mechanisms, right, to handle these complex heterogeneous graph structure. Okay, so here shows some sample results of our models, right? So this is a quite old result, right? It's already outperformed by many following works, right? But during at the 2019, right, it came perform best at different tasks like link operation task, node regression recommendation task, and node classification task, and so on. Right? So this is about the public data set and the task, right? But I'm more interested in introducing the how to use the heterogeneous graph neural network into different societal applications, right, or domain applications, right? Like this one, we actually apply the heterogeneous graph neural net to the opioid overdose prediction. So in the USA, the opioid overdose is a critical societal issue in the USA. So based on the patient prescribing data, we are able to build a patient prescribing behavior network, right? Like we have the relationship between different patient, different doctor, pharmacy, drugs, right? Then after building this is a typical, this is the patient prescribing record in the pharmacy, right? Then we have these patient profile information, drug information, and also doctor visiting information, drug taking information. So based on this historical prescribing record, we are able to build a patient. Actually, this is a dynamic heterogeneous graph, right? So for each patient the prescribing record, we are able to build a heterogeneous graph, right? That is the patient prescribing at T1. That is the patient prescribing at T2 and T3. So at different time steps, we are able to build a heterogeneous graph. Then after connecting the heterogeneous graph at different time steps, we are able to build this temporal heterogeneous graph. Okay, right. So then after building these temporal heterogeneous patient behavior graph or networks, right, then we can apply the similar idea that we propose in the heterogeneous graph to learn the feature representation of each patient, right? Then since we want to predict whether this patient will be overdosed in the near future or health in the near future, it's a typical classification task, binary classification task, either healthy or overdose, right? So after building these temporal heterogeneous graph, we apply heterogeneous graph neural net to learn the feature representation of each patient. Then we apply a typical classification model, binary classification model, to predict whether this patient will be healthy or overdose. Okay, so here are some experimental results on the real PDMP data. That is the real data of the prescribing data in the USA states. Okay, so here you can see the performance, right? This is the name of our model. We can outperform all kinds of baseline methods like a sequential model, the general graph neural network model, heterogeneous graph neural network model, temporal graph neural network model, and also some, the problem-related model. Okay, so here is a case study, right? If we look at these, the second figures, right? So there are two types of patients. The first one is high risk patient. The second one is the green line, the solid line shows the low risk patient. The yellow dashed line shows a high risk patient, right? So you can see that our model can correctly, clearly distinguish between high risk patient and the low risk patient, right? So these results are predicted by our model. It can clearly distinguish between high risk patient and the low risk patient. Okay, so this is the case study. And we also apply heterogeneous graph, enrich heterogeneous graph recently with language model for more societal applications, right? So for example, we apply the heterogeneous graph neural network model to Jack interaction prediction task, right? Like based on the public medicine data, we are able to build a medical knowledge graph. And based on these, the text data of public medicine and also the medical knowledge graph, we are able to combine the text data. So this is the text data, language modeling data. This is the graph data, knowledge graph data. Then we are able to fuse the language model layer and the GN layer, graph neural network model, to obtain the fused representation. Then we are able to then or to predict the missing link or the interaction link between any two jacks. Right? So this is an example of how we apply or enrich heterogeneous graph neural network model with language model for the Jack interaction prediction task. And also we apply the heterogeneous graph neural network model to the food recommendation or the recipe recommendation application. So based on some, food knowledge graph, food information, right? The recipe information, we are able to build the food knowledge graph. So food knowledge graph is a typical heterogeneous graph. Then after applying the heterogeneous graph on the food knowledge graph, build the food knowledge graph, we can learn the embedding of each user and the embedding of each food or each recipe. Then we are able to do the food recommendation to the target user. Okay, so this is another application. So by now I have, let me briefly summarize the research impact for the task one, improving the effectiveness of graph machine learning. So I'm currently quite active in improving the graph machine learning research, and our study on heterogeneous graph neural network or heterogeneous graph learning is one of the most influential works, right? Which has been widely used or cited in academics or industry, right? And we apply the heterogeneous graph neural network based technique to solve different societal applications, right? The work for using heterogeneous graph neural network for the opioid overdose prediction get the best paper award of SACM in 2021. Okay, so that is about the task one, improving the effectiveness of the graph machine learning, right? Then for the task two, I'm spend some time in improving the efficiency of the building graph machine learning model. Okay, so when we talk about the resource constraint challenge, there are two major resource constraint challenges that I work on. The first one is about data label level constraint. So data label level constraint means that, so usually collecting label data is a challenge or resource consuming, right? So here, these two figures shows, you can see this is the label distribution of a social network. It's obviously the long tail distribution. Means that a lot of nodes don't have labels, okay? So, and another is about limited label in the molecular graph. So we find that this is I think it's a molecular net data, a public, very popular public benchmark molecular data. So they are about, let me see, right? Yeah. About 20% of the molecular graph only have less than 20 labels, right? Okay. So I show these two figures means that the limited label phenomenon or limited label problem is very common in the real world data or real world application. So that is about the label level challenge. Right? The second one is about the model level constraint or model level challenges. Currently, graph data become larger and larger. Right? Like the largest open graph benchmark data has more than 100 million nodes, right? And we are trying to build some large graph foundation models with a lot of parameters, which is inspired by the large language model, right? We try to build some large graph foundation model with a lot of parameters. But, unlike the industry, right? OpenAI, they have lots of computing resources, right? I would like to say, unlimited computing resources, right? But in the academic labs or especially in the university, we only have limited computing resources, right? Like we only have some GPUs, right? And but a lot of real world application request real time inference or real time response, right? So how can we build efficient machine learning model that can train and infer faster? That is the model level constraint I try to solve. So based on these resource constraint, the first thing I work on is the label efficient graph machine learning. The second thing I work on is the model efficient graph machine learning. Okay, so for the label efficient graph machine learning, there are two typical techniques, right? The first one is called the graph self-supervising. The graph self-supervising, right, is quite similar to the idea of the current pre-training techniques, right? That means we only use the informative graph data information, but don't use any label information. of the graph to train the graph neural network model for downstream task, right? So there are two type of graph self-supervised learning techniques. The first one, the graph contrastive learning technique. So the major idea of graph contrastive learning is that given an original input graph, we do some data augmentation, like random delete some node or random delete some algae, or to do some attribute perturbations, right? Then we can obtain the two augmented graph and use GNN to encode two representation of two augmented graph and try to maximize the agreement of the embedding of these two augmented graph, right? So that is the major the idea of the graph contrast learning. So I have done some work about building some advanced graph learning contrast learning techniques, right? And the second typical technique of the graph self-supervised learning is called the graph generative learning. Graph generative learning is quite like the idea of the noise autoencoder. So given an input graph, we do some perturbation, like attribute perturbation. Then we use a GNN encoder to learn the representation of these perturbated graph. Then we introduce another decoder to reconstruct this graph, and we try to minimize the reconstruction loss between original input graph and the reconstructed graph. So that is called the graph generative learning, right? So I also did a little work about the graph generative learning. So that is about the graph self-supervised learning work that I have done, right? And the second thing is regarding the label efficient graph learning is called the graph fusion learning. So just now I mentioned graph self-supervised learning don't use any label information, right? But for the graph fusion learning, we suppose for each like for the node classification task, for each class we have few labels. We have fusion labels, right? So then the goal is to develop an effective graph machine learning model with fusion label node, right, as the supervision signals, right? So we propose a new research line called the graph fusion learning, right? So the major idea is, graph fusion learning is very popular in the image computer vision domain or the image processing domain, but before our work in 2020, right, there is no work about graph fusion learning. So we proposed the graph fusion learning research lines, right? And they did a lot of work about graph fusion learning, node level graph fusion learning, LG level graph fusion learning, graph level graph fusion learning, and also some survey work to summarize these three types of graph fusion learning. So we have done a series of work about the graph fusion learning. Okay, so yeah. I'm not going to talk about the details, right, due to the time limits. Only have about 10 minutes, okay? So yeah, now let me talk about the model efficient graph machining. Just now I mentioned about the label efficiency, right? If we don't use any label information, that is the graph self-supervised learning. If we use a fusion label for each class, that is the graph fusion learning, right? And for the model efficient graph machine learning, we try to improve or make the training time or the inference time of the large graph machine learning model faster. So that is the about the model efficient graph machine learning. So there are two techniques we majorly work on about the model efficient graph machine learning. The first one is graph neural network distillation. The second one is the graph neural network pruning. So the goal is to develop some efficient method to speed up the training or the inference of the graph machine learning model, while maintaining the competitive inference performance, right? Maintaining the competitive effectiveness. Okay, so the first model efficient graph machine learning we work on is the graph knowledgeization. So the idea of the knowledgeization is that suppose initially we have a large teaching model, right? Pre-training the large teaching models, right? Then we have another small student model. It can be GNN model or other smaller model like multi-layer perception. Then we just transfer, distill the knowledge from teacher model to the student model, right? Then after training the student model, right, we only need this small student model to do the inference. Since this small student model is much smaller than the original teacher model, right? Then the inference time of the student model is much faster than the original GNN model, right? Original teacher model. So that is the major idea of knowledgeization. Okay, so we have done some works about graph knowledgeization, right? So you can see that here is one method we proposed. It has the y-axis shows the effectiveness. The x-axis represents the efficiency. So if you can see that our model can achieve the similar effectiveness of the standard graph neural network model, but our model is about 1,000 times faster than the typical or than the general graph neural network model. So that is what we want to achieve. Much faster than the general graph neural network model, but have the close or the similar effectiveness of the general graph neural network model. Okay, so that is about the knowledgeization. Another technique to speed up the graph machine learning model training and inference is about the graph neural network pruning. So the idea of the pruning is that, so not all parameters in the graph neural network are necessary, right? We find that, right? And we only need to sample or identify a sub-neural network, sub-graph neural network. It's called a graph neural network winning tickets, right? To approximate the capability of the full graph neural network, right? By prune some to do the neural network pruning. This is the original graph neural network. It's fully connected, right? But we can do some prune. We prune some neurons or prune some connections or parameters, right? So then it can be sparse. It becomes more sparse graph neural network. Since they are much less parameter compared to the original graph neural network, these pruned graph neural network will be much faster in training and inference. So we have done some works about the graph neural network pruning. Okay. So then the next question, just now I mentioned about the data efficiency and the model efficiency, right? The question is, can we do join the data and the model efficiency, right? The answer is yes, okay? So join the data model efficiency means that we use less data and less parameters, right, to build a graph neural network model, right? So here we in the last year, ICML, we proposed a method called dynamic contrastive graph neural network pruning, right? So originally, the idea used the contrastive learning, right? So originally, we have a graph data, original input graph data. Then we do some augmentation, G prime, to augment the graph. Then we use graph neural network to do the graph contrastive learning. We get the contrastive learning loss, right? So after that, we compute the gradient value of the loss function with respect to each data sample. Right? Then we rank each data sample based on the magnitude of the gradient. We only sample a set of the data sample with the largest magnitude of the gradient value to train the model in the next epochs. Okay, let me talk more about the detail of the key design of this model, why it can be faster, why it can use less parameter, less data, right? At first, the backbone of this model is the contrastive learning model. Contrastive learning model means that we don't use any label to pre-train the graph neural network model. So then we achieve the first goal, use less label data, right? And we use the pruned graph neural network for the graph contrastive learning. So here we don't use the original idea of the graph contrastive learning. That's use the full graph neural network. We use pruned graph neural network model. That means we have less parameters, right? And again, the third step, we introduce the data sampling. That means at each step, we only sample a set of informative data sample into the next epochs of the model training, okay? So then we use the less data samples. So by using these unified, it's actually quite a simple model, right? But we can achieve the three goals. At first, we use less label information. We use less parameter. We also use less data to train the graph neural network model, right? So I think you should be clear about the motivation of contrastive learning and also GN pruning, because I talk a lot about contrastive learning and pruning just now. But why we also introduce a ranking mechanism to rank the data sample here, right, is supported by a theoretical series, right? So we find that the performance gap between the optimal model, suppose L theta star is a loss function of the optimal model. Hello, theta t is our design model. If we want to minimize the gap, performance gap between the optimal model and our model, we need to minimize this error bound, right? So this is the gap between optimal model and our model is bounded by these error terms. So this error term is defined by the difference between the gradient, the summation of the optimal model and our model chain on the subset data, right? So if we want to minimize this, that means we need to minimize this error term. We need to approximate this term to this term as much as possible, right? So this is the summation of the gradient value computed on the subset data. If we want to is this value approximate to this value as much as possible, we need to sample a subset of data that has the largest gradient values, right? If we can sample like if the 10% only 50% of data can gain like 99% of the gradient value, then we think this model can approximate the full model very good, very well, right? Okay, so that is the major ideas, right? We want to sample the data value, data samples, right? That has the largest gradient value, right, respect to the loss function. Okay, so that is the theoretical support of these step 3, right, or step 2, right? Step 3, this is a trick. This is the trick. I'm not going to talk about the detail, right? Because due to a time limit, you can read the papers if you are interested in these techniques. Okay. So let me show some results, right? This is our method, right? So you can see we can achieve the best effectiveness, right? The best performance over multiple graph classification tasks. This should be mutate protein. This should be the graph classification task, right? Our model can achieve the best performance. And also, our model uses only 50% of the data, 50% of data. And our model has the smallest smallest inference time compared to the baseline model, right? Okay, so that is about the resource efficient graph machine learning, right? So we also, beside the general benchmark data, right, or the public data, we also apply the resource efficient graph machine learning to some societal applications, right? So we have applied resource efficient graph machine learning to the drug trafficking detection on the social media data. So why we use resource efficient graph machine learning here is because the drug traffic label is quite challenging to obtain. So we only have few label data of the drug traffic. So we need to develop like a graph fusion learning, right, to solve this task, or some other resource efficient graph machine learning technique to solve this challenging task. Right? Here are some sample results about the drug trafficking detections, right? And also we apply the resource efficient graph machine learning to the drug molecular property prediction or the drug discovery applications. Okay? We also apply the resource efficient graph machine learning to like the malicious repository detection, which is a kind of application of malware detection. Okay. So yeah, we also enrich large language model with resource efficient graph machine learning for some NLP application, like the caption generation task. We can use the same graph contrast learning to improve the performance of caption generation. We also use some graph data augmentation to improve the some question answering application. Okay, so to summarize the research impact of this second, we are among the first group to study the resource efficient graph machine learning, right? And we applied resource efficient graph machine learning technique to different societal applications like opioid drug trafficking detection, molecular property prediction, malware detection, and so on, right? And we currently we are organizing resource efficient machine learning workshop at the KDD. Okay, so yeah, I have talked about improving the effectiveness and efficiency of the graph machine. So the last task is about improving the safety of the graph machine. So I work on 3 topics, right? The first one is the robust graph machine learning, how to handle the noise data and how to handle the attacking data. And the second one is how to build a fair graph machine to handle the biased data, sensitive data. And also the last one is how to build interpretable or explainable graph machine learning. Right? So here are some sample works about improve the robustness of the graph machine learning and also improve the fairness of graph machine learning or improving the interpretation of the graph machine learning. Right? So due to the time limit, I'm not going to discuss the details. Right? So to summarize, why my current research, lies in the intersection of AI, graph machine learning, and societal application. So I work on both core AI and applied AI research. For the core AI research, I try to improve the effectiveness, efficiency, and the safety of the graph machine learning using different techniques. And based on these fundamental core graph machine learning research, I try to apply the developed technique into different applications, into different domains, like the public health domain, right? Food recommendation, opioid overdose prediction, and also apply this technique to the cybersecurity problem, like malware detection, power plant failure detection, and also apply them to some science problems like molecular property prediction, drug discovery problems, right? So that is a brief summary of my current research. Okay. And so this work is supported by some faculty collaborator, my student, and funding from National Science Foundation, Brandeis University, University of Notre Dame. Okay, so thank you.
Thank you, Professor Zhang, for that enlightening presentation. And we can take one question from the audience. Anyone?
Thank you very much for the presentation. It was super interesting. I'm also working with graph neural networks, so I have a question related to at the beginning when you said that you added the temporality to the graph. Yeah. How much bigger did the graph network actually become by adding the time information?
How much?
Like what? The input. So before you said like you had different heterogeneous, you have like different inputs, and then you added temporality to the input.
So
right?
Yeah. So but we split them into different graph snapshots. So for at each time we only load one graph snapshot.
So you don't input like
no, we don't load the whole graph, right? At each time we have one graph snapshot, right?
Oh, okay.
Yeah.
Okay. And so how does it take into consideration previous? How much history do you get like to make the next prediction?
How much what?
History, like how many?
History. Yeah. It depends on the data. It depends on the data. Like if we consider the academic graph, I mean the citation graph, it can be like a 20 year or 30 year. Each year we have a snapshot of the graph. It can be 20 years, 30 years, or even larger. And for other graph, let me see what kind of other graph, right? We also have a COVID graph, like the connection between different, different state in the USA. Mm-hmm. I mean the transmission of people, the communication of people. I think that should be I didn't remember exactly. It should be 1 month. We have one graph snapshot, and we have about like 3 years data. It's about 36 time steps. Mm-hmm. It depends on the data.
Yeah. So yeah, if you take those snapshots when you make the input to the network, mm-hmm. how does the graph network change when you have to take into consideration the time? Like, are there big changes, or you just encode it like 1, 2, 3, 4, 5, 6, 7 as one extra feature? Because I imagine that if you have day 1, let's say, I don't know, temperature and humidity, day 2, temperature, humidity, day 3, temperature and humidity, and you bet that in a graph, your input becomes like much bigger. Yeah. So how that, like the model, the graph network takes it, like, I'm not explaining myself, I'm sorry.
Yeah, we can discuss.
Yeah, fine.
Later,
perfect. Thank
right?
You.
Okay.
Thank you very much.
No question about it.
Okay. Thank you, Professor Zhang.
Okay, thank you.